example, we have two wires separated by 10 centimeters. Each wire carries a current of 1.25 amps, but the current is flowing in opposite directions. Here we have an X, it means the current's into the page. Here we have a dot, the current is out of the page. The question is, find the magnetic field at point P. So there are two wires, there are going to be two fields. Those fields are vectors, so we have to find each magnetic field vector and then do the sum. So let's talk about wire 1 first. We'll call this guy wire 1. So it has current I1, 1.25 amps, which is flowing out of the page. We ask, what is the direction of the magnetic field due to this wire? We know that the magnetic field makes a big circle around the wire. So the wire's at the center, and the circle, the magnetic field, has to cut through point P. So that's what we're trying to find. What's the direction of the magnetic field? Well, we use our right-hand rule. Our thumb goes in the direction of current, and our curled fingers show the direction of the circle. So the magnetic field vectors everywhere are a tangent to this circle. At point P in particular, the tangent either points up or points down. We use our right-hand rule, so our thumb goes with our current, fingers go with our knuckles resting at point P, and we see that our fingers point up. So the magnetic field at point P points straight up due to wire 1. So there is B1. So let's find our vector B1, then after we'll find the vector B2, and then we'll do the addition to find the net magnetic field. So let's do the magnitude of B1 first. So the magnitude of B1, it's the magnetic field due to a long straight wire, so we can use our equation that it's mu naught times I1 divided by 2 pi times R1. R1 means the distance from wire 1 to point P. That distance is given as 10 centimeters in the diagram. So mu naught is 4 pi times 10 to the minus 7 Teslas meters over amps times current I1, 1.25 amps, divided by 2 pi times R1, 0.10 meters. Put that through the calculator and we get a magnetic field strength of 2.5 times 10 to the minus 6 Teslas. So there's the magnitude of our field. Magnetic field is, of course, a vector, so we should write this as a vector. Let's think about our components. So let's put our x and y coordinate system the usual way. Positive x to the right, positive y to be up. So our x component of this vector is 0. b1x equals 0. Our y component of the vector is positive because it points up, and it's the whole thing. b1y equals plus 2.5 times 10 to the minus 6 Teslas. So our magnetic field is going to be 2.5 times 10 to the minus 6 J hat in Teslas. So there's our magnetic field due to wire 1. Next, we'll find the magnetic field due to wire 2.